class. Today we will discuss on the following objectives. The first objective would be to find out the difference between the Langrangian descriptions, which we have covered in the previous class, and the Eulerian descriptions, which we will study in this lectures. And second one would be to find the strains in terms of the Eulerian descriptions. The difference between the Langrangian and the Eulerian description is that Langrangian descriptions refers to that of the original configurations, whereas the Eulerian descriptions describes in terms of the deformed configurations. The difference between the Langrangian descriptions and the Eulerian descriptions. In the Langrangian descriptions, the displacement field or the displacement vectors is in terms of the initial coordinate system, which is the undeformed configuration. So undeformed configurations will be in the forms of x, y, z and t. So the coordinates of the deformed configurations, the coordinates of the deformed configurations would be x dash, y dash and z dash will be related to the initial configuration, which is the undeformed configuration. So the initial configurations will be in the forms of x, y, z and t. Similarly, y dash, which is the deformed configurations, will be related to the initial configurations, which is in the undeformed state. It is in the forms of x, y, z and t. Similarly, the z coordinates will be in terms of the undeformed configurations or the initial configurations. The initial configurations are in the forms of x, y, z and t. The second definitions that we have is the Eulerian descriptions, which is again in this case the displacement field or the displacement vectors is given in terms of the deformed configurations. So it is in the forms of x dash, y dash, z dash and t. When we compare it with that of the Lagrangian description, it was in terms of the initial coordinate systems or the undeformed configuration. Over here the displacement vector u is in terms of the deformed configuration. The deformed configurations are x dash, y dash and z dash. So in such a case the x coordinate is referred with respect to that of the deformed configuration, which is x dash, y dash, z dash and t. Y coordinates will be represented as x dash, y dash, z dash and t, and z will be represented in the forms of x dash, y dash, z dash and t. So it is in the terms of the deformed configuration. So we have first definitions is in terms of the Lagrangian descriptions and the second one is in the forms of the Eulerian description. So in order to have a unique solution, so this sets the Lagrangian description will give us one set of the solutions, then the Eulerian descriptions will give us the next set of the solution. Now this solutions has to be unique. In order to have a unique solution, we need to have one-to-one correspondence to the displaced configurations and the original configuration. So we need in both the cases the Lagrangian descriptions as well as in case of the Eulerian description, we need to have the one-to-one correspondence. Then only we can have a unique solution in both the cases. Either we choose as the Lagrangian descriptions or we choose it as the Eulerian descriptions. Now again, this is the three-dimensional coordinate system, the Cartesian coordinate systems in the forms of x, y and z. At t is equal to 0, this one is the configurations which is shown by the bold lines. Now at t is equal to t, we have the deformed configuration which is shown by the dotted line. The point A lies on the state of the body at t is equal to 0, and point A dash lies on the body shown by the dotted lines. U is the displacement vectors, R dash is the final position vector of the point A dash, and R is the initial position vector of the point A. So in terms of the Langrangian descriptions, the coordinates x, y and z will be referred to as in the context to the deformed configurations. So what will be the deformed configuration? It will be with respect to the coordinate a dash. So the coordinates of the a dash would be x dash, y dash, z dash at time t. Similarly, the y coordinates will be represented in the forms of the displaced configuration, which is x dash, y dash, z dash and t. Similarly, z will be represented in the forms of x dash, y dash, z dash and t. So all these coordinates x, y and z are under the under deformed conditions. So we have written the coordinates which are x, y and z under deformed configuration. So this is the difference between the Eulerian descriptions and the Langrangian description. In case of the Langrangian description, we have written all the things in the terms of the initial conditions or the undeformed conditions, but in the case of the Eulerian description, we write everything in terms of the deformed configuration. So in such a case, we can write the values dx, dy, dz on the similar lines as we have done in case of the Eulerian descriptions, as relating the undeformed configurations with respect to the deformed configurations. The deformed configuration would be in the form of dx dash, dyz, dy dash and dz dash, and the undeformed configuration would be in the forms of dx, dy and dz. This one is a matrix which is the displacement gradient matrix. This notation for this displacement matrix is given by term H matrix. So this matrix is again the partial derivatives of coordinates x with respect to x dash, the partial derivatives of x with respect to y dash, or you can say y prime, the partial derivatives of x with respect to z prime, the partial derivatives of y with respect to x prime, the partial derivatives of y with respect to y prime, the partial derivatives of y with respect to z prime, the partial derivatives of z with respect to x prime, the partial derivatives of z with respect to y prime, and partial derivatives of z with respect to z prime. In all the formulations, we need to calculate the values of strain. So this one ds whole square is the final is the initial displacement. So initial displacement, how we can write? Again we can write it in the forms like this, which is dx prime multiply dx prime, dy prime and dz primes multiplied by h transpose multiplied by h transpose into the dx prime, dy prime and dz prime. This is the similar thing what we have earlier done in case of the Langrangian description. The same thing over here we have done. Then again what we need to calculate? We need to calculate the strains. So initial we have calculated ds square. Now we need to calculate the values of ds dash square. So how we will calculate? So again we will do the same formulations what we have done over here. So ds prime will be what? It will be again ds dash dy dash and dz dash multiplied by this terms again dx dash, dy dash and dz dash. And if we subtract the values ds square, we will get the identity matrix over here. So we will get the values of ds dash whole square minus ds square is equal to dx dy dz multiplied by identity matrix minus h transpose h multiplied by dx prime dy prime and dz prime. Now we are interested in calculating the values of the strains. The strains would be were in the forms of dx dash square minus ds square divided by ds prime whole square. So if we compare it with that of the Langrangian descriptions, at that point we had at the denominator ds square, but over here we have ds prime whole square. This means that we are defining the strains in terms with respect to the deformed configuration. So if we carry out the formulations, we will get the values of ds square minus ds square divided by ds dash whole square is equal to 1 by 2 multiplied by identity matrix minus h transpose multiplied by h. This h transpose is the displacement gradient. Now this entire terms is known as the E. This entire term is known as the E, which is known as the Eulerian finite strain tensor, which is again equal to I minus H transpose H. Now we define this terms H transpose H, this term as the Cauchy strain tensor. In the case of the Langrangian descriptions, we have defined F transports as green strain tensor, but in case of the Eulerian descriptions, H transpose H is defined as the Cauchy's strain tensor. Now we know x prime is equal to x plus u, relating the initial configurations with that of the deformed configurations with the values u being the displacement in x directions. Again y dash would be equal to y plus v is the displacement that is occurring in the y direction, z dash is equal to z plus w, w is the displacement that is occurring in the z direction. With these equations we are relating the initial configurations with the deformed configurations. Again we will do the same steps as we did it for the Langrangian description. This is an homework from that needs to be done from your side. The same steps that we have discussed in the context of the Langrangian description, the same steps we will do over here, and finally we will get the values of h as I minus k. So what is the k? K matrix. K matrix is given by the partial derivatives of u with respect to x dash, the partial derivatives of u with respect to y dash, the partial derivatives of u with respect to z dash. Again the second row, the partial derivatives of v, which is the displacement in y direction with respect to x dash, the partial derivatives of v with respect to y dash, the partial derivatives of v with respect to z dash, and again the third row, the partial derivatives of w with respect to x dash, the partial derivatives of w with respect to y dash, the partial derivatives of w with respect to z dash. Now we can write these equations, the similar thing what we did in case of the Langrangian descriptions, as 2e we have derived previously in the previous slide, which is equal to k transpose plus k minus k transpose k. So finally if we rearrange the terms, we will get the Eulerian descriptions of the strain as 1 by 2 k transpose plus k minus 1 by 2 multiplied by k transpose k. So in this case the values represented by k transpose plus k is the linear terms, and the values represented by k transpose multiplied by k is the non-linear terms. Now the comparisons and the important conclusions from the Eulerian and the Langrangian descriptions. The Eulerian descriptions was defined as E is equal to 1 by 2 K transpose plus K minus 1 by 2 multiplied by K transpose K. In this case, this terms was known as the linear terms. This term is known as the linear terms, and this terms is known as the non-linear term. If we compare it with that of the Langrangian description which we have discussed, the Langrangian description is given by 1 by 2 J plus J transpose plus 1 by 2 multiplied by J into J transpose. In that case, the values J plus J transpose is known as the linear terms, and J multiplied by J transpose is known as the non-linear term. Now we will discuss what will happen if the displacements are very small. If the displacements are very small, then the higher order terms will vanish. So in case of the Eulerian description, which is the higher order term? So this one is the higher order terms. For a small displacement, for very small displacement, these terms would be 0. Similarly, in case of the Lagrangian descriptions, if the displacements are very small, then again the higher order term. So this one is the higher order term. The entire terms is an higher order term. It will turn to 0. So we can conclude one important fact. Under the case of the very small displacement, these Lagrangian descriptions will converge to that of the Eulerian descriptions. So in the case of the very small displacement problems, which means the infinitesimal small displacement, whatever the results we get from the Eulerian description will converge to that of the Langrangian description. So these types of the theory dealing with such theory are known as the infinitesimal deformations theory. This means that if the deformations are very small, then the theory dealing with such descriptions is known as the small displacement or the infinitesimal deformations theory. And if we consider the nonlinear terms, these nonlinear terms, these terms and these terms, then we will deal with the finite strain theory. But over here, if we are neglecting the higher order terms, we will be dealing with the infinitesimal deformations theory. So the learning outcome for this session is that we have demonstrated the difference between the Lagrangian descriptions and the Eulerian descriptions, and when in which context these Lagrangian descriptions will converge to the Eulerian descriptions. If the displacements are very small, then in those cases we do not make any difference between the original or the deformed configurations. So problems dealing with such cases would come under the infinitesimal small, which means the small deformations theory. The next we discussed regarding the Eulerian description, which deals with the deformed configurations. This is all for this session. We will meet you in the next session. Thank you.